Hello everyone, my name is Abhishek TR and today I will be presenting my experiment on multi-cylinder diesel engine under the course robust design. This work was done under the guidance of Dr. Bhartish sir. Let's dive into the details of the study. And what all we covering today are, I'll start with the introduction, followed by the objective of the study. Then we will discuss the apparatus used, the experimental procedure, and the data collected. We will also go through the experimental design and methodology, the analysis process, procedure, results, and finally the conclusion. And the introduction about multi-cylinder diesel engine is this study focuses on analyzing how load and speed influences fuel consumption in the multi-cylinder diesel engine. We aim to determine their impact on the time required for 10 cc of fuel consumption using statistical methods. Multi-cylinder diesel engines are commonly used in automobiles and industrial applications because they offer better efficiency and power. However, performance varies based on load, speed, and other operating conditions. Objective. The main objective of the study is to develop a regression model to predict fuel consumption time based on load and speed. Using ANOVA, we analyze the significance of these factors. This result helps optimize engine performance while reducing the need for excessive experimentation by predicting outcomes through statistical modeling. And apparatus. The apparatus required are to conduct this experiment. We used a multi-cylinder diesel engine test rig which is there in our thermal lab. The key instrument include a digital speed indicator for RPM measurement, a fuel flow setup using a burette, an eddy current dynamometer for load application, and a temperature indicator to monitor cooling water and exhaust gas temperature, and also a stopwatch to indicate the time for 10 cc of fuel consumption. And the procedure of conducting experiment are, first we have to ensure that the adequate fuel in the tank and connect the cooling water system, and then we have to start the engine and use the starter switch to stabilize the engine at 1500 rpm and record the initial data, where measure speed, fuel consumption rate, and temperature at no load condition, and apply load on different stages. Increase load using dynamometer and maintain the required speed. And measure the fuel consumption time. Use a burette and time stopwatch to record the time in seconds. And similarly, repeat for all the different readings. Perform tests for all combinations of load and speed. And this is the tabular column. This table represents the experimental data collected, where we systematically varied load and speed to measure fuel consumption time. The structured data help in further analysis. And the experimental design and methodology. For this study, we used a full factorial design with two factors, load as a one factor and speed as a other factor. I have taken load in four levels, that is 10, 20, 30, 40 Newton meters, and speed at five levels, 1000, 1000, 1000, 1200, 1400, 1600, and 1800. And this results in total of 20 experimental runs. We then apply regression analysis and ANOVA to interpret the data and optimize engine performance. Analysis procedure. We will see the analysis procedure using the Minitab software. First, open Minitab and click Stat DOE Factorial. Here, click on Create Factorial Design, and our experiment have two factors, so I'm going for general full factorial design with two factor, so I'm keeping number of factors as 2 and click design display available designs. Okay, and go to designs, change the A into first factor, that is load, Newton meter, and the second factor is speed, speed RPM, and I'm taking the load in 4 levels, so I'm adding it as 4, and speed and 5 levels, so in 5, and number of replicants keep it as 1 only. Click OK. Go to factors. Here you can see there are four factors, four levels in the load, and there are five levels in the speed. Click OK and create fact here results. In results, the summer table option should be checked, and options, the randomized runs and store design in worksheet should be checked. Click OK. Click OK. And Minitab creates a tabular column by reordering our levels and factors. So you can see here factors, there are two factors, and the runs is 20, the total runs is 20, and there is also 20 experiments. Now what I am doing is, here the load and speed which are there in the tabular are not same as our speed and load, so I am replacing this load and speed with my data. So I'm going to Excel to copy those data. Here you can see I have taken the readings from the multi-cylinder diesel engine experiment from the thermal lab, and I'm copying it. Control C, and replace these two columns with those data. They are replaced. Now add the response in the tabular column, and our response is time taken for 10 cc of fuel consumption. I'm adding it as time t, and go to Excel and copy the values and paste this in the response column. Now the response is added. Click on the time t heading and go to stat, again DOE factorial. Here click on analyze factorial design. Here select time t as the response and click on select button and go to terms and add this AB, this is the multiplier, to the available terms and click on OK. Convergence, keep it like this only. Options also same. Size also same. And graphs, I'm going to plot all the histogram, normal plot, residual, and residual versus fit, and residual versus order in a single plot. So 4 in 1. You can click all of them to add them separately, and also check the residual versus variable and click OK and go to results. Here keep it as the same, don't change anything, and go to storage. Here check the fits and residuals and click OK. OK. Here you can see the Minitab has created fits and residuals, which is the difference value, and also ANOVA table, the analysis of variances. Here you can see the ANOVA table, analysis of variance and factors. The load I have taken in 4 levels, 10, 20, 30, 40, and speed in 5 levels, 1000, 1200, 1400, 1600, and 1800. This is the model summary. The R is 85. And also you can observe the p-value 0.000, which is acceptable. And regression equation. Uh, this is calculated by full factorial regression. And this all data is in this all data also created using full factorial only. And this is the Pareto chart, and these are the four residuals, histogram, and also residual versus weights, residual versus frequency versus residual versus observation order, and mm, what is the final step is we have to add the intersection tables. Go to stat, DOE, factorial, factorial plots, click on them, and keep the load and speed as the factors. Here change the terms to display to all terms, and options remains unchanged. And in graphs, confirm that both main effects plots and interaction plots are checked. Click OK. Wave model, there is no change. Time is the response. And click OK. Minitab has generated main effects plot and interaction plot. In main effects plot, we can see both load and speed are separately shown, but in interaction, the both factors are combined here. This is the difference between them, and this is the process of analysis using Minitab. And these are the results that are obtained. These are the tabular results which are obtained from the Minitab. This table presents the raw experimental data collected for different load, speed, and RPM conditions. And the load, time, and speed that are the load and speed are the factors we given, and the time is the response and fits the predicted value obtained from regression model in Minitab, and also residuals. This is the difference between the actual experiment value and the predicted values, which helps in checking the accuracy of our model. The data was later analyzed using ANOVA and different statistical plots. And these are the results related to analysis and regression models. And in Minitab, I used full factorial analysis to obtain the regression model. Here you can see the regression model, that is time t, and also R square is 90.82 percentage, indicating a strong model fit, and also p-value is less than 0.05, confirming that load and speed significantly affect fuel consumption and time. And this is the Pareto charts of the standardized effects. The Pareto chart shows the magnitude of effects of different factors. Here we see that the load and speed are the most influential factors affecting fuel consumption time. The taller the bar, the greater the impact of the response variables. Residual plots for time. These residual plots includes four of the graphs: normal probability table, and also residual versus fitted table, and also histogram, and residual versus order. And overall, these plots confirm our model is statically sound and free from major biases. This is the main effects plot for time. The main effect plot shows how load and speed influence the fuel consumption time individually. Fuel consumption increases with load, a direct relationship. Fuel consumption decreases at higher speed at 1800 rpm. Fuel consumption is where the fuel consumption is lowest. This confirms that operating at higher speed with lower loads improves efficiency. And this is the interaction plot for time. The interaction plot helps in identify if the effect of one factor depends on other. No strong interaction between load and speed. Here you can see that there is no strong interaction. This indicates the minimal interaction. This means we can optimize load and speed independently to achieve fuel efficiency. And finally, the conclusion. Through this experiment, the experiential learning multi-cylinder diesel engine, which systematically analyzed the influence of load and speed on time using statistical tools. The Pareto chart helped us identify the most significant factor, while the main effect plot showed clear trends in how load and speed individually affect time. The interaction plot revealed that dependencies between these factors, proving that there is effects are not purely independent. And the residual plots validator our model's reliability, confirming normality, randomness, and absence of the autocorrections in error. The data tables provide a structured view of our observation, ensuring accuracy in the analysis. And overall, this study not only depend on our understanding of engine performance, but also reinforced the effectiveness of statistical techniques in experimental validation. These insights can contribute to optimization in real engine applications, making operations more efficient and reliable. Thank you.